Have you ever really stopped to think that, well, everything around you, the chair you're sitting on, the air you're breathing, maybe even you might not be quite as solid and static as it feels?
It's a pretty wild thought, isn't it?
It really is. What if, deep down, it's all just vibrations, ceaseless movement? That's what we're getting into today. The big question is, what are these minute vibrations that make up matter?
Yeah, what does that actually mean?
Exactly. So our mission for this deep dive is to explore the source material, the vibrational universe, a synthesis of waves, matter, and space-time. We're going to trace this idea of vibration through like 4 major eras of physics.
From classical waves right up to, well, the really strange stuff.
Right, and see how this concept keeps changing, showing us a universe built less on static stuff and more on these dynamic nested vibrations. And there's this key idea, superposition, that ties it all together.
It pops up everywhere.
It really does. So stick with us. We're aiming to give you the shortcuts, those aha moments, maybe make you see the world just a little bit differently by the end.
Hopefully.
Okay, let's start where it feels most normal, most intuitive. The classical world. Vibrations we can actually see and, well, feel.
Right. Classical vibration is basically just something oscillating, moving back and forth around a point of equilibrium. And it's everywhere.
Like what? Give us some examples.
Oh, sure. Think of a pendulum swinging, or, the hum you feel from a big machine, or even just your car engine vibrating.
Right.
Even huge things like bridges vibrate. Wind can do it. Traffic even. Famously, soldiers marching in step. That's a real thing engineers worry about.
Yeah, I bet. So they're either trying to damp these things down, stop buildings from shaking apart.
Or sometimes harness them, like in musical instruments or speakers.
Okay, so how do physicists usually break down these classical vibrations? Are there different types?
Yeah, typically 3 main kinds. You've got free vibrations, like plucking a guitar string once it rings at its natural frequency. Then forced vibrations, where you keep pushing it, like continuously bowing a violin.
Okay.
And damped vibrations, where friction or air resistance makes the swinging die down over time. But the really critical thing here is resonance.
Ah, resonance. That's when things get dramatic.
Exactly. If the frequency of your push, your forced vibration, matches the system's natural frequency, boom, the amplitude can skyrocket. That's why soldiers break step-crossing bridges. You don't want to accidentally hit the bridge's resonant frequency.
Right, that could be bad. Very bad. So that's a localized oscillation. How does that become a wave, like sound traveling from that guitar string?
Yeah.
And what happens when waves meet?
Well, that local wiggle pushes on the stuff next to it, which pushes on the stuff next to that. And so the disturbance propagates outwards. That's your wave. And when waves meet, this amazing thing called the superposition principle comes into play, at least for most everyday waves, what we call linear systems. It just means the total effect is simply the sum of the individual waves at that point.
So if you have wave A and wave B where they overlap, the result is just A plus B.
Pretty much, yeah. The displacement just adds up. And the most remarkable thing is, after they pass through each other, they continue on completely unchanged. It's like they were never there for each other, except for that brief moment of adding up.
That's wild. They just pass right through.
They do. And this adding up is what leads directly to interference.
Okay, wait. If they pass through unchanged, how do you get interference patterns like loud spots and quiet spots with sound waves?
It's all about how they add up during that overlap. If 2 crests arrive at the same point at the same time, their amplitudes add bigger wave. That's constructive interference.
Okay.
But if a crest from one wave meets a trough from another, they subtract. If they're equal and opposite, they can completely cancel each other out right at that point. That's destructive interference. It's just simple addition and subtraction moment by moment.
Okay, that principle of adding waves seems fundamental. But then comes Fourier, Jean-Baptiste Joseph Fourier. He gave us the mathematical tools to, pick apart complexity, right?
He really did. Fourier's theorem is, it's groundbreaking. He showed that any complex waveform, no matter how weird and wiggly, can be perfectly described as a sum of simple sine and cosine waves, pure tones, essentially.
So you can break down any sound or signal into basic ingredients.
Exactly. That's Fourier analysis. It lets you find the harmonic spectrum, which simple frequencies are in there, and how strong each one is.
Okay, so you have the fundamental frequency.
That's the lowest one, yeah, the main pitch you hear. And then you have harmonics or overtones, which are integer multiples of that fundamental.
And that mix of harmonics is what makes a trumpet sound different from a violin, even playing the same note.
Precisely. That's the timbre, the unique sound quality. A pure sine wave sounds very plain, almost sterile. But a trombone, It's got the fundamental plus a whole specific recipe of harmonics layered on top through superposition. That's its richness.
And you can go the other way too, right? Build complex waves by adding simple ones, Fourier synthesis.
Yep. You can mathematically construct, say, a sharp square wave by adding up an infinite series of specific sine waves, the odd multiples, with decreasing amplitudes. Or a triangle wave using cosine waves. It's incredibly powerful.
This also brings up the idea of two ways to look at the same signal, doesn't it? Time versus frequency.
Absolutely. You can plot how the amplitude changes over time. That's the time domain, what you'd see on an oscilloscope trace. Or you can plot how much energy or amplitude there is at each specific frequency. That's the frequency domain, what you'd see on a spectrum analyzer.
And the Fourier transform is the magic lens that lets you switch between those views.
Exactly. It's the mathematical tool to go from time to frequency and back again. They're not different signals. They're just two different but equally complete ways of describing the same information, like looking at an object from the front versus looking at it from the side.
So why does this matter to, us?
Well, think about high-fidelity audio. To reproduce a sharp sound, like a cymbal crash, accurately, the system needs to handle high frequencies really well because those sharp changes in the time domain are made up of lots of high-frequency sine waves in the frequency domain.
Ah.
And here's something amazing. Your own ear, specifically the cochlea inside, acts like a biological Fourier analyzer. It physically separates incoming complex sound waves into their different frequency components along its length before sending that information to your brain.
Wow. So my ear is doing Fourier analysis right now.
Constantly. It's how you distinguish different sounds, different voices, different instruments. Pretty neat, huh?
That is seriously cool. Okay, let's shift gears dramatically. We're leaving the world of tangible classical waves and taking, well, a quantum leap.
Into the weird zone.
Definitely the weird zone. Here, classical ideas break down, but vibration, oddly enough, becomes even more fundamental. Matter itself starts acting like a wave.
Yeah, historically the line was very clear. You had particles, tiny localized things like billiard balls, and you had waves spread out disturbances like water ripples. Mutually exclusive.
Until experiments just blew that apart, like the photoelectric effect.
Right. Einstein explained it by showing that light, which everyone thought was purely a wave, actually delivers its energy in discrete packets, like particles, photons. And the energy of a photon depends on its frequency, its color, not the light's intensity. That's particle behavior.
And then the flip side happened with electrons, right? Things we knew were particles.
Exactly. Davison and Germer shot electrons through a crystal and got a diffraction pattern. That pattern, the way the electrons spread out and interfered, is undeniable wave behavior. Electrons were acting like waves.
So, things can be both, particles and waves.
That was Louis de Broglie's radical idea. He proposed that all matter has this wave-particle duality. Everything has a wavelength related to its momentum.
Even me, I have a wavelength.
You do, but because you're macroscopic, your mass is large, so your momentum is large, and your de Broglie wavelength is incredibly ridiculously tiny. Far too small to ever notice or measure. But for tiny things like electrons, the wavelength is significant enough to cause observable wave effects.
Okay, mine's starting to bend. So how does quantum mechanics describe this dual nature? What replaces the classical wave?
It introduces the wave function, usually written as psi, the Greek letter ben. This is the mathematical object that contains everything you can know about a quantum system's state. And crucially, it obeys the Schrödinger equation.
Which is a wave equation.
At its core, yes. It describes how this wave function evolves in time, and its form confirms the fundamental wave-like nature of matter at this level.
But, and this is the big leap, right? This wave function isn't a physical wave like a water wave.
No, not physically waving in space. Max Born gave us the interpretation that's still dominant today. The wave function itself isn't directly physical, but its square gives you the probability density of finding the particle at a particular point if you were to measure it.
Probability density, so it's a wave of chance.
Exactly. It's a wave of probability amplitude. The vibration here isn't physical stuff wiggling. It's the mathematical potentiality, the likelihood of different outcomes that's waving and evolving according to Schrödinger's equation. The total probability of finding the particle somewhere always has to add up to 100%, which is called normalization.
Okay, that's abstract. And superposition, how does that work here? It must be even weirder.
Oh, it is. In quantum mechanics, superposition means a system can literally be in multiple distinct states at the same time. Not just waves adding up, but like an electron in an atom being in a combination of energy level 1 and energy level 3 simultaneously.
Until you look at it.
until you measure it. The measurement forces it to choose one state, but before that, it exists in that probabilistic blend of possibilities.
The double slit experiment is the classic example, isn't it? Even with single electrons.
The perfect example. You fire one electron at a time. Classically, it should go through one slit or the other, but its wave function goes through both slits simultaneously. The electron's state is a superposition of went through slit 1 and went through slit 2.
And the wave functions from each pass interfere.
Exactly. Those two possibilities interfere, creating the interference pattern on the screen behind, even though only one electron goes through at a time. It's interfering with itself, or rather, its possibilities are interfering.
Okay, wow. And Fourier comes back here too. How does that fit in?
It's fundamental again. What we picture as a localized particle is actually understood in QM as a wave packet. Think of it as a superposition, an adding up of many, often infinitely many, simple waves with different momenta, but which interfere constructively in one small region of space and destructively everywhere else.
So a particle sitting here is really a bunch of momentum waves combined.
Precisely. The wave function describing its position and the wave function describing its momentum are a Fourier transform pair. A tightly localized particle, narrow in position space, is made up of a very wide spread of momentum waves, broad in momentum space, and vice versa.
That sounds familiar, like the time and frequency domain thing.
It's the exact same mathematical relationship, and the really crucial quantum difference is that this superposition, this wave packet, is the reality before you measure. The particle is spread out in momentum if its position is well defined. Measurement then collapses this wave packet, forcing a specific outcome.
So the vibration is like a vibration of mathematical possibilities that only becomes real when we poke it.
That's a pretty good way to put it, yeah. The vibration is in the realm of potentiality described by the mathematics.
And this connects directly to the Heisenberg uncertainty principle.
Directly. It's not just about faulty measuring tools. It's a fundamental consequence of the wave nature and the Fourier transform relationship between position and momentum. You cannot have a wave packet that is simultaneously sharply peaked in position and sharply peaked in momentum. The mathematics forbids it. The more precisely you know one, the less precisely you inherently know the other.
Because a narrow packet in one domain requires a wide spread in the other domain, according to Fourier.
Exactly. It's baked into the fundamental wave nature of matter.
Okay. My brain hurts slightly, but in a good way. Let's go deeper still. Quantum field theory, or QFT, you said this is where particles stop being the main characters.
That's the big shift, yeah. Quantum mechanics was hugely successful, but it wasn't fully compatible with Einstein's special relativity, and it struggled to describe processes where particles are created or destroyed, which happens all the time in particle accelerators.
So QFT came along to fix that.
Oh, by doing something pretty radical, it said. Forget particles as the fundamental things. The fields are fundamental. The universe is filled with underlying fields, an electron field, a photon field. That's the electromagnetic field, quark fields, etc. One for each type of particle. These fields exist everywhere in spacetime.
Okay, so fields are the bedrock reality now. What are particles then?
Particles in QFT are just localized excitations vibrations, really in their corresponding field. Like a ripple spreading across a pond, an electron is a quantized ripple in the electron field. A photon is a quantized ripple in the electromagnetic field.
Quantized meaning it comes in discrete chunks.
Exactly. You can only excite the field in specific energy steps, and each step corresponds to one particle. This view elegantly handles particle creation and annihilation. You're just adding or removing excitations from the field.
And this explains why all electrons are identical.
Perfectly. Because they aren't individual little things, they are all excitations of the exact same underlying electron field. That field permeates the entire universe, so its excitations are naturally identical everywhere.
Okay, that makes a strange kind of sense. And interactions, like two electrons pushing each other away.
That's seen as an interaction between their fields. Specifically in QFT, forces are mediated by the exchange of other particles, which are themselves excitations of other fields. So two electrons repel each other by exchanging virtual photons, excitations of the electromagnetic field. We draw these interactions using those famous Feynman diagrams.
Virtual photons. As opposed to real ones.
Yeah, virtual meaning they are temporary intermediate particles that pop into existence just to carry the force and then disappear. They don't have to obey all the same energy rules as real particles we can detect directly.
Okay, QFT is painting a very different picture. Fields vibrating. But what about empty space? What's the vacuum in QFT? Is it just Nothing.
That's one of the most mind-blowing parts of QFT. The vacuum is not empty. It's defined as the lowest possible energy state of all these quantum fields. But because of the uncertainty principle, again, even in its lowest energy state, a field can't be perfectly still and have zero energy simultaneously.
So even the vacuum is vibrating.
It is. It's constantly undergoing tiny, fleeting oscillations called quantum fluctuations. These are often visualized as virtual particle-antiparticle pairs constantly popping into existence out of the field's energy, existing for an immeasurably short time, and then annihilating each other.
Empty space is a sea of particles appearing and disappearing. Seriously.
Seriously. The vacuum is seething with this activity. It sounds like science fiction, but we have real, solid, experimental evidence for it.
Like what? How can you prove something like that?
Well, take the Casimir effect. You put two uncharged metal plates incredibly close together in a vacuum. What happens? They get pushed together.
Why?
Because the tiny gap between the plates restricts the kinds of virtual photons that can pop into existence there. Only certain wavelengths fit. Outside the plates, all wavelengths are allowed, so there are more virtual particles pushing on the plates from the outside than from the inside. It's the pressure of the vacuum fluctuations. Lemereau measured this tiny force in 1997.
That's incredible. Pressure from nothing.
Pressure from the vibrating vacuum, yeah. And there's more. Things like the Lamb shift, a tiny shift in the energy levels of the hydrogen atom and the anomalous magnetic moment of the electron, a tiny correction to its magnetic strength. These effects are measured with astonishing precision. And they can only be explained if you include the interactions of the electron with the sea of virtual particles in the vacuum. The QFT calculations, including these vacuum effects, match the experimental measurements to something like 10 or more significant digits.
Wow.
It makes QFT the most accurately tested theory in the history of science. It's powerful evidence that this seemingly empty space is actually a dynamic, vibrating entity.
So the journey continues. Solid stuff became particles, particles became probability waves became field excitations. The vibrations are now in these abstract fields we can't see.
Exactly. Substance keeps dematerializing the deeper we look. And what's beautiful about QFT is its mathematical elegance. It's built on fundamental principles like symmetries called gauge symmetries. And a deep theorem by Emmy Noether connects symmetries directly to conserved quantities and, in QFT, even necessitates the existence of the force-carrying particles. It's like the universe follows this incredibly strict predictive grammar.
A symphony with very specific rules. Okay, one final step. The edge of known physics, maybe beyond. String theory. This takes vibration to the ultimate level, right?
It aims to, yes. The big problem QFT couldn't solve was incorporating gravity. General relativity, Einstein's theory of gravity, just doesn't mesh well with QFT. At the quantum level, you get nonsensical infinities when you try to combine them.
So string theory is the hopeful candidate for a theory of everything. What's its core idea?
The absolute core idea is revolutionary. Stop thinking of fundamental particles as zero-dimensional points. Instead, propose that the most fundamental constituents of reality are unimaginably tiny, one-dimensional vibrating loops or segments of energy, strings.
Not points, but tiny vibrating lines or loops. How tiny are we talking?
Almost incomprehensibly tiny. The Planck length, around 10 other meters. If you blew up an atom to the size of the observable universe, a string would be about the size of a tree on that scale.
Okay, that's small. Why does changing points to strings help with gravity?
Because interactions are different. Points trace lines in spacetime, and their interactions happen at single points, which causes mathematical problems. Strings sweep out two-dimensional surfaces, world sheets, and their interactions are smeared out in a way that smooths out those infinities, allowing gravity general relativity to be incorporated into a quantum framework. That's the huge technical advantage.
And the connection to particles. If everything is strings, where do electrons and quarks come from?
This is the beautiful part, the ultimate vibrational universe idea. All the different fundamental particles we see, they are not fundamentally different things. They're all just the same fundamental string, vibrating in different ways.
Like different notes on a violin string.
Exactly like that. The way the string vibrates determines the particle's properties. Its energy of vibration determines its mass through EMCLA. Other properties, like electric charge or spin, are also encoded in the specific pattern of its vibration.
So the entire zoo of particles is just the music of these tiny strings.
That's the vision, a profound unification. One single fundamental entity, the string, whose different vibrational modes generate everything we observe.
And does gravity fit naturally into this music?
It does, and that's a major reason for the excitement. When you analyze the possible vibrational modes of these strings, you find one that has exactly the properties predicted for the graviton, the hypothetical quantum particle that carries the gravitational force. So in string theory, a gravity isn't tacked on. It emerges naturally and necessarily from the theory itself.
Okay, that sounds incredibly elegant, but there's always a but in theoretical physics, isn't there? You mentioned controversy.
There is, yes. It's crucial to be clear about its scientific status. String theory is, right now, more of a mathematical framework than a fully tested physical theory.
Why is that? What are the main hurdles?
The biggest one is the lack of testable, falsifiable predictions. The energies needed to directly probe the Planck scale and C strings are astronomically high, way beyond any conceivable experiment currently.
So no direct proof. What about indirect hints?
People look for indirect evidence, like hypothetical cosmic strings left over from the early universe, or specific patterns in the cosmic microwave background radiation, or the existence of particles predicted by extensions like supersymmetry. But so far, nothing conclusive has been found, and many of these potential signals aren't unique to string theory anyway.
And there's another issue, right? Something about extra dimensions.
Yes, that's a big one. For the mathematics of string theory to be consistent, it typically requires more spatial dimensions than the 3 we experience, usually 6 or 7 extra dimensions, making a total of 10 or 11 space-time dimensions.
Where are they then?
The idea is that they are compactified, curled up into incredibly tiny, complex shapes at every point in space, too small for us to perceive directly.
Okay, but what's the problem with that?
The problem is the number of ways these extra dimensions can be compactified. Current estimates suggest there could be something like 10 to the power of 500 different ways to do it.
10 to the 500.
That's a lot, an astronomical number. And each different way of compactifying leads to a different possible universe with potentially different particles and different physical laws. This is called the string theory landscape.
So it predicts everything, which means it predicts nothing specifically.
That's the criticism. If there are 10 or agree possible outcomes, how do you find the one that describes our universe? How do you make a unique prediction that could be tested and potentially falsify the theory? It makes the theory incredibly difficult to pin down experimentally.
So the debate is whether it's truly science or more like mathematical philosophy.
That debate is very active, yes. Is it a predictive theory of our universe or an incredibly rich mathematical framework that might contain the right description, but we don't know how to find it or test it yet?
Still, the idea itself.
Yeah.
That physics might ultimately be about the geometry of these tiny hidden dimensions.
Yes.
It's fascinating.
It is. It suggests the fundamental laws of nature might just be consequences of the universe's shape at the very smallest scales.
Right. Let's try to pull this all together. We've been on quite a journey watching the meaning of vibration get deeper and, frankly, weirder at each step.
We started classically with physical wiggles, things actually moving back and forth, and waves just adding up simply.
Then quantum mechanics turned vibration into a wave of probability amplitude, a mathematical description of possibilities that exist in superposition until measured.
Quantum field theory then made the fields themselves the fundamental reality. And particles became quantized vibrations or excitations of those fields, even in the vacuum, governed by deep symmetries.
And finally, string theory, at the edge, proposes that everything, all particles, all forces arises from the different vibrational modes, the different notes of tiny fundamental strings in extra dimensions.
From physical ripples to probability waves to field excitations to string harmonics, it's a profound shift.
The big takeaway, the aha moment perhaps, is that this solid, stable world we experience seems to be just an emergent phenomenon. It arises from this incredibly complex, layered cosmic symphony playing out underneath.
And the rules of that symphony, the laws of physics, get more unified, but also much more abstract and mathematical the deeper we probe.
Yeah, further and further from our everyday intuition. So here's a final thought to leave you with. How does it feel really internalizing that the most solid object near you right now is, at its core, just relentless, patterned vibration?
What does it mean for how we understand reality when the deepest laws seem to be written in a language of abstract mathematics and hidden geometry, perhaps forever beyond our direct grasp?
Something to definitely think about as you go about your day in this, well, fundamentally vibrational universe.